different thing. And that's what there really is. I can't tell you stories in detail about how people do research, except about myself. It isn't polite, and furthermore, I really cannot get data on other people, how Einstein did things. Most people don't really get down to the nitty-gritty of how things go. So I'm forced to do this, talk about myself, and you will find, I think, that I am trying to underline a couple of points. One is that if you will do a little extra work each time and get down to fundamentals and study things until you understand them, then Pasteur's remark, luck favors the prepared mind, will favor you. That's really what's going on. So let me start first with the history behind my involvement in digital filters. I had a vice president, W.O. Baker, who I had very much admired, but in all my years there I was never in his office, and I don't think he ever came to mine. We would meet in the hall, and we would talk briefly. One time when I met him, I said, Bill, when I came to Bell Labs in '46, we were going from relays to electronic central offices. And there were a large number of old relay people who would not learn to use oscilloscopes or anything else like that. They were moved over to a location I mentioned where, and I said, to you they were an economic loss because they had to be getting out of the way, and to me they were a social loss because they were very disgruntled and unhappy. Then I went on. During the war, Bell Labs had developed at our military location analog gun directors and plotting boards and everything else. There were a great many expert analog people. When we came into digital machines, I watched a large number of analog people unwilling to convert. And I said, this same thing happened. They have been pushed aside, walked around and evaded, and they're an economic loss to you and they're a social loss to me because some of my friends are not really happy. And I went on and said, you and I know, and this was back in the early 70s, the telephone company is going to go digital as fast as it can. If we do not now lay down books and other things so people can convert it when they're young, we will have even more people intellectually lost because of change and socially unhappy. Because when the world passes you by, you are not a happy person. Well, he looks me square in the eye and he says, yes, Hamming, you should, and walks off. Well, I don't like digital filters. I don't know anything about it. But as I walk back to my office, I say, do I wisely ignore my vice president's remark? And in any case, even if he hadn't said it, considering the arguments I gave, should I neglect the importance of this topic? Obviously, I should do something about it. So I went to my friend Jim Kaiser, who I knew moderately well at that time, and said, Jim, you are the world's expert practically on digital filters. You wrote your doctoral thesis on it and so on, and you've done all kinds of work. There comes a time in people's career when they should stop and summarize it, write a definitive book that gets it all down where people can find the whole thing instead of scattered in 25 different papers. And he allowed I was right. And I said, fine, why don't you write a book? He said, well, okay. I started monitoring it. He wasn't doing anything. I started fussing at him. Nothing. I finally said to Kaiser, tell you what, we'll go to lunch together 4 times a week at least in a restaurant, and you will teach me digital filters, plus a little bit in your office, and I'll write the first part and you can write the advanced part. And we'll call it Kaiser and Hamming. He said, fine. So I start learning digital filters from him, and there's quite a few stories I can tell you about crazy things that happened, and I will tell you a number of them. But he isn't writing anything. I finally say to him, hey, Jim, if you don't write more, we're going to call Hamming and Kaiser. He says, fine. When the stuff is finally done, I say to Jim, you have not written one word. I'll call it Hamming. I'll thank you in a preface. He says, fine. We're still good friends. So that's how I came to write the book. It was because of social conscience that something needed to be done. I did not want to do it. I tried to get out of it. I could not get out of it. I did that which needed to be done. But let me tell you, jump ahead a bit, what are consequences? I started well into the writing. I phoned up UCLA summer division extension courses and said, hey, wouldn't you like a course on digital filters next summer? Because I wanted to get some debugging and going through the notes before I turned it into a book. I want to get a practice. They said, fine. Well, I would say for maybe 10 or 15 years, I went out to Los Angeles, week or 2 weeks, sometimes I taught 2 courses, to give a course. And each time they paid me $5,000 about, or a couple times more. But because it was popular there, I have given the course in Paris, in London, at Cambridge, England, at Nova Scotia, at Toronto, and innumerable places in the United States, generally at the price of $5,000 for a week. Not bad for something you didn't want to do. Furthermore, the book has gone through 3 editions, and I haven't any idea how much I've made, but it must be a comfortable amount if it's gone through 3 editions. If you do that which society wants and needs, society frequently recognizes it and repays you somewhat. So one of the lessons is you don't always do what you want to do. You do what you believe needs to be done and needs badly. So that's one of the consequences. Now, let's go back to the learning business. I'm a mathematician, basically. I discovered immediately that they were always using Fourier series to fit functions throughout electrical engineering, as you know. I said, well, any complete set of functions, Bessel functions, Matthew functions, any complete set of functions will represent, as anyone else, any set of functions you want. Any continuous function will represent just as well in one set as another, practically. Why always the frequency approach? Well, you know, Kaiser, great expert he was, and he's a very smart man, really didn't answer it. I asked a bunch of other ones. One electrical engineer said, well, you know, alternating current is sinusoidal. That's why we use sinusoids. I said, you're out of your mind if you think it's got anything to do with signal processing. Well, I don't know how much you people know. If I really put it to you, why do you use those instead of other ones? I give you the answers, but it took me a long while to find them. If you want time invariant system, such that whether I do it today or tomorrow, I will get essentially the same result, then the eigenfunctions of translation are indeed the sines and cosines, or preferentially the complex exponentials. Second, if you have a linear system, dynamic one, the eigenfunctions are again the complex exponentials. I finally extracted those out of books, but I also extracted a third one, which is going to be important. We are going to sample equal spaces. From the samples, we ultimately want to reconstruct the function. If, as I will show you in a few minutes, I have equal space data and I have a pure sinusoid of high frequency, it will be aliased into a pure frequency of low frequency. One sinusoid will go into one sinusoid. That's not true of polynomials. If I have a high degree polynomial, say degree 15, and I sample 10 points and try to extract a 9th degree polynomial going through it, the relation is going to be very, very messy of the coefficients. High degrees of x don't go to low degrees of x under sampling at equal spaces. But for the sinusoids, they do. So those are 3 reasons why. Now let me remind you what an eigenfunction is. You have a system, you put it in, it emerges exactly the same, scaled by some factor. You had that when you took differential equations. You had that when you took linear algebra. It had matrices. They were the same thing. Very, very common idea. Well, when I put in a frequency into a network theory, what do I get? what you learned is a transfer function. I said, but isn't really what we're talking about the eigenfunction? I tried on a lot of engineers. All I got was, well, yes, if you want to call them eigenfunctions, you are. The transfer function is the eigenfunction, but we call it the transfer function. I said, why have two names for the same thing? The students have already had it in 2 courses. Why change the word? Habit. So the famous transfer function which you have is nothing else than the eigenvalue of the corresponding eigenfunctions. Pure and simple. It took me a long while to find out those fundamentals. Next, I want to go on to sampling. Let's see, if I have a frequency now, I've got to back up. You will sample at very many different rates. But we're going to sample at equal spaces because that's what you could build equipment for, and that's what you do almost all the time. I will immediately make a transformation so I'm sampling at unit times. 0, 1, 2, 3, 4. Thus, whether you're working in microseconds or in years, I will have the same equations. And therefore, I will be able to see what you are talking about microseconds and what some economists are talking about years is the same thing once I bring it down. So I'm always sampling t equals 0, 1, and if you want some negative values, all right, but I'm sampling at the integers. Well, this is, as you know, cosine pi, 2 pi n, and we call it some other number, n k we'll say, kt sine 2 pi at, oh, cosine, minus sine. Well, the sine will be 0. The other one will be 1. That any integer multiple will always drop out, and I will have this will be equal 1, and I will have the cosine. So that if I sample a high frequency equal spaces, I will get a lower frequency out. Right? In fact, I can get it all the way down to the a could be 0 and 1, or if I want to write a, if a is bigger than a half, I write 1 minus a in place of a. I can get the interval from minus a half less than equal to the frequency a less than 1/2. The endpoints we can argue about some other day. And this is Nyquist's theorem, old man Harry Nyquist, who also, remember, did several mechanisms of stability. A great man who could do 2 things. You don't meet him very often. He was a very nice guy and a very smart guy, but he had his goofy ideas too. What I am saying is that all high frequencies, when I sample, become a frequency in that interval. We can argue about the endpoints in a moment. It is the act of sampling. Now, Chucky called it aliasing. A high frequency alias under a low frequency. It goes under a different name. Now, network people usually carry all those high frequencies along, but I said to myself, once I have sampled, I have only low frequencies left. I cannot find those high frequencies unless I have outside information. Now, I went over this thing backward and forward, roundabout, and looked at the n values and so on, and understood what happens to the n values. If I have a sine at the highest frequency, or the lowest one, you'll get all zeros. So you couldn't tell what amplitude the sine was. So the sine term can't be worked. Now, I want to say something else about what probably your professor didn't tell you. When I work in sine and cosine, I have a pair of eigenfunctions. The sine and cosine, and I have only the interval here to 0 up there, but I have 2 functions. When I use a complex exponential, I have 1. Now, in the real case, 0, the constant term, is a single eigenvalue, and all the rest in sine and cosines are double eigenvalues. Whereas if I go to complex ones, they're all uniformly a single eigenvalue. And that explains to you, really, if you studied very hard, why it is in electrical engineering e to the ix works so much better than cosine plus sine. It works out much better. You remember it? Always magic everything come out much easier. That's the reason behind it all. It's a simpler eigenvalue representation. Well, I want to dwell on this point. The sampling produces this aliasing. It is an artifact of sampling. A high frequency will appear as a low frequency. And you can do it any number of ways. It's a trigonometric identity. You could draw a high frequency and sample low rate, and you'll see it's equivalent to a low frequency. It's any number of ways of doing it. The simplest one is a trig identity. No more, no less. Well, I got it finally into my head. And you have to have 2 samples for the highest frequency present, and at the ends you can't do it. You have to have at least 2 samples for the highest frequency present. Now let me digress and tell 3 stories about how, merely knowing that, I did useful things. The first one was I got trapped in doing a 28th order system of ordinary differential equations, which was simulating a Navy intercept plane coming in on a target. Now, I've got to know the step spacing I'm going to use in my integration numerically in order to know how many steps I'm going to do. They want 25 trajectories, and they know roughly in real time how long they would be. Some of them are longer flights than others. I had that information, what flights they want me to simulate. If I have to take a step size twice as small, the computation is twice as big, right? But I have to give them a reasonable estimate. I finally give an estimate. It turns out $25,000. I think I can do the job. Fine, they say, here's the money, let's see you do it. And I spent a good piece of 1 year, and the lady who worked for me spent the whole of a year trying to get those answers. But what size? The theory of all the differential equations methods you know of will express the step size in terms of the 5th derivative of something. With 28 equations, who is going to tell me any reliable 5th derivative? No way. But you see, when I'm calculating a solution of a differential equation, I am calculating samples, equal spaces. So I go to them and say, hey, because of the sampling theorem, if there's high frequency, I'm going to have to sample very fine. If there's low frequency, I can take a big step. What is the highest frequency I have to worry about? They went back and retreated, and next week they come around and said, well, 10 cycles. If there's anything above 10 cycles, we'll worry about, but you better take care of everything below 10 cycles per second. Well, that tells me I got to have some sampling rate. Now, if I had samples from minus infinity to plus infinity, this applies. I certainly don't have them from minus to plus. I've got only samples up to now, so that's roughly a factor of 2 off, so I must have something like 4. Furthermore, I'm only using when I use my formulas to calculate the next point. Again, only a few old values, so I say, oh, it must be something like 8. But do I know? So I did the obvious. One, I took the second order differential equation y second plus y equals 0, and took the initial condition, which gives a cosine, and started calculating for various step sizes how accurate I could get it. Next, I sat in my office with paper and pencil, and I derived theoretically what it would be. And lo and behold, the two agreed. At 7 samples per step size, I was getting reliably something like 4 or so figures per step. Now, of course, they don't know the weight of an airplane or something exactly to the pound. They don't have 6-figure accuracy of anything. So I don't have to calculate too accurately. 17 marginal. 10, quite safe. For any accuracy they knew, I was perfectly safe with 10. So I gave the bid. Well, when we finally get the program going, $8,000 of programming costs into the business, because we're programming absolute binary. I asked the girl to run the thing at 120th of a second. I figure 70 is about safe, but merely. She does. I asked her to run the same thing again at 1/60th. The solution is no good. It's a mess. It doesn't resemble the other one. I asked her to run at 1/80th. The answer at 1/80th and 120th agree pretty well. So I say to myself, my theory has been verified. So there you have, the sampling theorem alone enabled me, with some thinking and a little other things, to calculate this important question: how much is it going to cost to solve your differential equations? What sampling rate must I use? The second story goes, a friend of mine has just come back from West Coast, and he says to me, Douglas, who's a subcontractor, is using a 100 to a 10,000th, a 1,000th to a 10,000th of a second step size in order to launch a Nike missile. I laughed right in the spot and said, that's absolutely ridiculous. If he's using that, if he's using a 10,000th of a second step size, he's worrying about 1,000 vibrations per second. Well, the stick model he's using couldn't possibly support that. The atmosphere doesn't have that. If he'd been following the vibrations of frame, yes, but not an airplane like that with the stick model he has. So my friend says, why? And I explained to him exactly the kind of thing I told you now. The sampling rate is being what it is, and the vibrations being the kind of thing it is. They're off. They're crazy by something like a factor of 100. Well, he goes back out. He says they're wrong. They look into things. They have a number in the register over 7 bits. 120 times too large. They're calculating the wrong problem. 100 times more expensive than needed. Debugged across a continent. Right? The third one concerns here. I was here, and I was dealing with a very nice guy down the hall who was very smart, and he left. And his replacement wasn't too bright. I'm not going to name names, because he left too. He comes into my office one day and talks about sampling and the trouble we're having. And what they're doing is they're taking a very high frequency signal, modulating it down, sampling, and trying to go ahead and calculate what that signal is. Well, let's go back to this and see what that thing is. If I imagine frequencies, and that's the place where the frequencies start being aliased, this curve becomes more. This point comes from there, this point comes from there, this point comes from there, and so on. All these points here are algebraically added here. That's the way it goes across. Well, I tell you, you really don't need to do this stuff. He says he knows the sampling theorem, and I look him square in the eye and said, I know the sampling theorem better than you do. After all, I knew good old Harry Nyquist. So after some more arguments, I beat him down to the following simple observation. If he has out here signal and elsewhere there is none, and if this is brought back, shall we say, to here, from here to here, then the active sampling will demodulate the signal back down to low frequency. Right? We have hot arguments over that for another day. Finally, the man agrees to try it. He removes this huge rack of demodulation equipment. The thing runs better. If your signal will fall in one of these bands out here, then sampling will demodulate it down immediately, and you're down where you can play with the thing, because at those high rates, you can't calculate anything. You have to calculate so many steps, you'll spend all your life getting nothing. You can bring it down. Now, if that thing falls in a band like this, where the high is at this end and the low is that, then, of course, the frequencies are interchanged. And Bell Labs did the following. They took the voice, modulated way up, and then sampled to bring it back down in reverse order. So whatever you spoke, what was high frequency was low, what was low frequency was high. And it was kind of hard to understand what a person said. But they tried it with music and various other things. They had a great deal of fun. You can do these things. if you understand the sampling theorem. Now these are 3 stories only illustrating what I told you. If you will understand fundamentals, like what that actually aliasing is, and understand that's due to sampling, then luck favors the prepared mind. This guy finally got a patent on this on radio and so on. He's going to demodulate it by that method. He didn't know what he was doing, so he never paid much on it. Now you know modulation, which I don't need to discuss, is multiply by a frequency, a cosine of frequency, and you get a product of 2 cosines is half the cosine of a half the sum plus cosine of a half the difference. No, cosine of the sum and the cosine of difference. Half cosine of the sum plus cosine of difference is the cosine cosine. So that if I take your low cosine frequency, multiply by a high frequency cosine, I'll get 2 frequencies. And if I drop the lower one, I have all the information in the higher band. That means, and the telephone company first did it, if I take a voice and move it up there, I can then add below a voice at normal voice level, ship them both over the same wire, at the other end, separate them by a filter, and then demodulate down, and lo and behold, I can get 2 voices across the continent on 1 wire at the same time. I suppose most of you are familiar with it, but that's how it came about. The whole business came about because the telephone company wanted to make more efficient use of the wires it had. And for across the country, the modulation up and filtering, modulation down again, paid. It doesn't necessarily pay on local phone calls. But you know the trick. It's done widely. Therefore, I'm going to want a lot of filters, which I will call low pass or high pass. I either want to pass the high frequencies and stop the low frequency, get the high frequency one, or get the low one, stop the high frequency. I want to stop one or the other. That's what are called filters. Now before that, I get into filter theory, which I'm headed for. I got to talk about least squares. Now in principle, you people know least squares, but bitter experience has taught me you don't. So I'm going to assume I've got some data at 5 equispaced points, -2, -1, 0, 1, 2. And I want to get a straight line, least square straight line through that. And I want to replace those 5 values with the one on the curve is the smooth data point. That's my idea. Well, it's not hard to do. But it's got its complications. If those are the actual observations, these are the UK, I want the difference. Remember, t is only going to be at the integers, -2, -1, 0, 1, and 2. I want that difference squared, k running from -2 to 2, to be minimal. That is what you believe with least squares, right? And most of you believe least squares is a good thing to do. I'm not saying it is. I'm saying most of you believe least squares is a real good thing. The sum of the squares, the difference between the signals and this. In other words, the sum of the squares of these little distances shall be minimal. Now comes the thing you frequently don't understand. This minimum function is a function of A and B. The t and the k are being summed, like t is really k, because t is going to take on the values of k. The variables are A and B, so I differentiate this minimum with respect to A and the min with respect to B. Now if I do that, I will get 2 times the square bracket UK minus A plus BK times the derivative of A, which is -1, equal to 0. I can throw away those 2 parts, and this is summation UK is summation A plus summation B, well, B times summation T. But T was picked cleverly. -2, -1, 0, 1, and 2, so that's 0. The summation A is a constant summed 5 times. That's going to be 5A. A is going to be the average. UK all over 5. So the average of the 5 values is the best least squares estimate. And conversely, incidentally, if you want if the best estimate is the mean, then you're working in least squares. That's due to Gauss. Now, if instead of a linear one, I had tried to fit a quadratic, I would have had differentiating respect to A, which would be the same thing. It would be summation UK equals summation A plus B summation T K plus C summation K squared. Oh, sorry. Yes. I'll get a 2 and a minus 1 for respect to A. Whoops, this. I will get this. When I differentiate respect to A, when I differentiate respect to B, I'll get summation K UK is summation Ka plus B summation K squared plus C summation K cubed equals 0. Oh, sorry, not equals 0. And I will have, when I differentiate respect C, K squared UK is K squared A plus B summation K cubed plus C summation K fourth. Well, all the odd powers are going to drop out because I picked them symmetric. So I only have these two equations. And I only want A. And when I do this, I will get A is 1 over 35 minus 2, or was it 3? I don't. Minus 2 or minus 3, I can't remember. So long ago, I seem to forget these things. Minus 3, 12, 17, minus 3. Plus 12 UK minus 1 plus 17 U minus 2, U minus 1, U0 plus 12 U1 minus 3 U2, all over 35. And the sum of the coefficients is 35. Here I got them all 1, and this was nothing else than U1 plus U minus 1 minus U minus 2, U minus 1 plus U0 plus U1 plus U2, each with a coefficient 5. Now you can look at this formula as a window. This one, every one of the 5 values, I look at those 5 values, I multiply by 1/5. When I'm using this one as a window, I multiply this value by minus 3, 12, 17, 12, 3. I did it for one position. If I shift it over one, the same formula will apply. So I have a window. I'm looking at the thing. The window looks at 5 values. If I want the best least squares fit straight line, I will use that window. If I want the best least squares fit for a quadratic, I will use this window. This introduces the whole idea of window. You are looking at the data through a window. You never see nature itself. It's always through a window, usually the instrument, but sometimes the window is your head, your inability to think. You impose things on what you see because you think that way, and therefore that is what you see. You never really get to see reality. There's always some kind of an instrument between you and it. It depends upon the instrument, has different characteristics. The window looks different, but you're always looking at a window. Now, if I'd done it for n values, by the way, now I want to know what happens when I put a pure frequency in those. You will find out that for the linear one, the window is going to be sine 3/2 t over 3 sine t over 2. If I took 5 points, it would be 5 there and a 5 there. If I take n points, 2n plus 1 points, there would be an n there and an n there. And this is that window, essentially a continuous window of what you're going to have. Those are the same numbers. When you sum up the result of putting a frequency in, you'll get this back. This is a response to a frequency, whether it's perfectly harmonic or not. This is the transfer function. This is the eigenvalue. Now you see at t equals 0, there's a 0 here, 0 there. You say, oh yeah, L'Hopital's rule. Let me differentiate the numerator with respect to t and denominator, and then evaluate as 0, and lo and behold, you get 1. Otherwise, you have something like this. You remember you're only going to go out to 1/2 in t if you're going to do it that way. I should have made another remark. In calculus, you use radians and natural logs. In practice, you use base 10 and degrees. In filter theory, you work in rotations. I have to work in calculus in radians because you know why. You took calculus, you know radians are the thing that works. Because the derivative of the sine is on the cosine. Any other units, the derivative of the sine has got some multiplier in front of the cosine. So that's why we use it. I've always got shifter rotations. By and large, I'll shift up to a half a rotation. So this is really going to be a half a rotation when I work in rotations. And this is the amount that gets through. It says, at that frequency, I get 1. That frequency, I get nothing. That frequency, I get negative. The higher ones, if I get ones will go like that. More and more wiggles. These over there will look like these, except there will be more tangent there. They'll have about the same amount of wiggles, but there'll be much more tangent here when I fit quadratic. If I fit another one, they'll have more derivatives at the origin. Nice. So the higher a polynomial I fit, the more tangency I get near the origin, but I cannot avoid those wiggles. They will be there. So that is what is happening. I get these eigenvalues, which are going to these are the multipliers of the corresponding frequency. You give me the frequency here, I multiply by that. Now this causes a great deal of trouble. Oh boy. I haven't got enough time to go through it. I should have. Well, I have to do some rushing. For smoothing filters, what I did, I will find that the plus and minus coefficients are always the same. For a differentiator, AK, or CK, is minus C minus K. For a smoothing filter, CK equals C minus K. And this one, of course, C0 is 0. This one, C0, is arbitrary. Now, there's a very simple formula. F of x equals f of x plus f of minus x over 2 plus f of x minus f of minus x over 2. It's algebra your children could even do. This is an even function. This is an odd. Every function is a sum of an even and odd function. Every filter design is a sum of a smoothing formula and a differentiator. If I can do those two, I can do anything because of this very elementary formula here. Now you know that thing. When you had Fourier series, which I'm going to have to rush through rapidly, you remember the expansion was in cosines and sines. It was in odd terms and even terms, right? Every function was a sum of even terms and odd terms. Fourier series said so. The sines were the odd terms, the cosines were the even terms, along with cosine 0, which is 1. Sine 0 is 0. Now I'm going to briefly go through. You remember Fourier series, they were orthogonal. That is, if I took any one of the sines or cosines with integer frequency, integrated over a whole period, if the two frequencies were the same, I got pi, and the two frequencies were not the same, I got 0. If I multiply a sine by a cosine, I'm bound to get 0 because one's odd, one's even. If I did the same with cosines, I got the same kind of thing. The difference was, at 0 frequency, I got 2 pi instead of pi, and therefore, habitually, one writes in a Fourier series, f of x is a0 over 2 plus a1 cosine x plus b1 sine x plus a2 cosine 2x plus b2 sine 2x, and so on. One writes this so that the formula for calculating the a's will be exactly the same. Otherwise, you got to remember the first one has a factor of 2 removed. Nothing great about it. Now the functions I'm going to want to do, you remember the ak and the bk are given by 1 over pi, the integral from 0, or from minus pi to pi, we'll say, f of x cosine kx dx. And there's a corresponding one for sines. But since I'm going to want, for smoothing filters, I will either want to pass a frequency or stop it. This function is either 1 or 0. For a while it's 1, then for a while it's 0. There's no question that you can do those things with the most elementary calculus. If it's a differentiator, that function is x. Using integration by parts, you can do it. So there really isn't any question in practice that I will have any trouble laying my hands on those a's and b's. They're there. What I have to do and rush through is make a statement that if I expand a function in Fourier series, I get certain coefficients calculated this way. Suppose I wanted to represent the best least squares fit. What coefficient would I have? Answer, the Fourier series. Now this is true of any orthogonal system. Orthogonal systems merely mean one function times another, multiplied by a positive weight function if you want, will give 0 if the two functions are different, will give you a number, wherever it is, when they are two of them are the same. You get pi in Fourier series of all the ones you get other numbers. But you get very simple things. Those are the multiplier values are the lambdas you divide by later on. The important thing is that for any set of orthogonal functions, the best least squares fit is the Fourier series. For Fourier series, or they are equivalent calculation of Fourier coefficients for any orthogonal system. We have that very nice property, which we're going to need next time. I've only touched slightly on what you do in Fourier series because I got to get started. The thing I got you reminded you of least squares. And this theorem, which is sort of proved in notes, I've had to gloss over. And I've also introduced this idea of a window. A window is a set of coefficients which you look at. It's 0 outside. You look at the signal with those weights. That's all you see. You don't get to see the individual numbers. You only get to see a window of some width, of some shape. And don't let me worry about a window having a negative coefficient. Window is a way of speaking. That -3 doesn't worry me. But I say everything you do will be that way. And I will have to introduce you to quite a few things that will be explained in terms of this window business. So I got you through, but the main thing I wanted to say is how much it paid me when I got into the business, not to go along with Kaiser and say yes, 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 but stop and say, why the frequency approach? What is this aliasing? What is this? And drag my feet until I understood. I told you 3 stories, the great payoff of merely understanding what the sampling theorem really was about. Now I admit, I told you I knew Harry Nyquist to some extent. He was a nice guy. You do tend to pay more attention to results named after friends of yours. So maybe you can argue, well, Hamming is lucky he knew Harry Nyquist. But I didn't know him that well. He was in West Street and I was out in Murray Hill. And I think that I had spotted it, once I'd worked with John Tukey for a while, that the sampling rate was vital, that I had to understand that thoroughly. And you saw a payoff. I say this happens all the time. So I see you next week. I got somebody down here for something. Okay, let's go home. See you next week. Oh, sorry, Friday, Thursday, Tuesday, Friday, 3 o'clock Friday.
Sorry, I was late today. I got caught eating lunch.
That's all right.
But there's a church function tomorrow, and I was wondering if I don't show up for class.
I can't do all. What I'm going to do is pass this thing around every Friday. Expect an initial. You miss 1 or 2 of them, I won't care. But if you miss every Friday, there'll be some difficulty.
Okay.
Yeah, same thing. Same question we had. So.
One day, anyone, 1 or 2 days, I don't mind. But if you miss every Friday from now on in, I'm not going to be happy. After all, I don't have any final or anything else to go on.